This is AP Calculus 4.5, Part 1. We're doing related rates word problems. These are geometric word problems that you may have to deal with. As we start this section off, it's really important that you know real common geometric formulas. So here are some commonly used formulas in this section. It might be a good idea to pause the video now and jot these formulas down to make sure you know what they are. I think these are all of the ones that are in the examples that I use. But if we're in class and you don't know a formula and I've left it off this list, all you have to do is ask. I'll give you a formula. That's not a big deal. But just know for the AP test that won't be available. Okay, so we're going to do the first example. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second, and I left off length here. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? All right, so I like to write down when I'm doing a problem like this the information that they gave me and the information that we are trying to find. So let's see, we know we're working with the area of a rectangle. So I know the formula that I'm going to use is area equals length times width. Next, I'm going to jot down what are they asking me to find. So what are they asking me in the question to find? Well, they want to know how fast is the area of the rectangle increasing. Well, if they're asking me how fast the area is increasing, they want the change in area with respect to time. So that's what we're trying to find. And then what did they give me? The length is increasing at a rate of 8 centimeters per second. So they gave me the change in L over time, and that is 8 centimeters per second. And it's positive because it's increasing. And then they say the width is increasing at a rate. So they're giving me the change in the width over time. It's increasing at 3 centimeters per second. And again, it's positive because it's increasing. And then they give me the length is 20. So at the time that we're talking about, the length is 20 and the width is 10. They want to know how fast the area of the rectangle is increasing. Okay, so we're going to have to use implicit differentiation here. We're going to take the derivative of all of these variables with respect to time. So when I do that, I have dA over dt is equal. Now, for this, I'm going to have to use the product rule. This is my first thing. This is my second. So using the product rule, derivative of L is dL over dt times the original second part, W, plus the original first part, L, times the derivative of the second part, and remember we're doing that implicitly again, dW over dt. And then at this point, I can just start plugging in the information that they gave me. We don't know dA over dt. That's what we're trying to find. dL over dt, that's a change in length. That was 8 centimeters per second. The W at the instant they're talking about was 10. L, the length at the instant they were talking about, was 20. And the change in width is 3. And then we would just do the math. That's 80 plus 60. So the change in A over time, the change in area over time, is 140. Now, we're talking about area, so think about units for area. We know it's centimeters, but isn't area going to be centimeters squared? And that's per second. So that's how fast the rate of the area is changing. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and width is 10 centimeters, how fast is the perimeter of the rectangle increasing? You may notice that this one is very similar to the last example that we did, but the only difference is that instead of talking about area, this time they're talking about perimeter. And the measurements in this rectangle are the same as in the last problem. Let's talk about what they're asking us to find and what they gave us. It says, how fast is the perimeter of the rectangle increasing? So we know the perimeter is going to be increasing, so it'll be a positive. We know that the perimeter formula for a rectangle is perimeter equals 2L plus 2W. 2 times the length plus 2 times the W. And so if they're asking us to find the change in perimeter over time, and they gave us that the length of the rectangle is increasing at a rate, so dl over dt is increasing at 8 centimeters per second, and the width dw over dt is increasing at a rate of 3 centimeters per second. And it says when the length is 20 and the width is 10. So they're giving us L is 20 and the width is 10. So what we're going to do is we're going to take the derivative implicitly. So we've got dp over dt, the change in perimeter over time, is equal to 2 dl over dt plus 2 dw over dt. And then we would just plug in to find our answer. So change in perimeter over time is equal to 2 times dl over dt is 8 plus 2 times dw over dt is 3. So dp over dt is 16 plus 6 or 22. Perimeter is a length, so we don't need square or anything. It's just going to be 22 centimeters per second for our rate of change. It is a positive 22. We would expect it to be positive because it did tell us that the perimeter was increasing. A 25-foot ladder is leaning against the wall of a house. The base of the ladder is moving away from the wall at a rate of 2 feet per second. A, how fast is the top of the ladder moving down the wall when the base is 7 foot from the wall? And B, find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. All right, with this one, we have a ladder leaning against a wall. We'll just say that this is the ladder. And this is the wall, this is the ladder, this is the floor. That is forming a right triangle there. And if this is the case, we know from the reading, we know this is the ladder. It is 25 feet. The base of the ladder is moving away from the wall. So that ladder, the base of the ladder is moving away from the wall. And let's say this would just be a Pythagorean theorem, if you think about, because we're talking about the length of the sides of this right triangle. So in the Pythagorean theorem, I'll label this one as A, this side as B, and this side as C. Well, C here is 25 feet from what the length of the ladder is. Now, if you think about this C value is not going to change because the size of that ladder is not getting bigger or smaller. It's not increasing or decreasing. That size of the ladder, if you think about it, is staying the same. It's just falling down the wall, scooting out this direction, and it's still going to be 25 feet for the entire problem. And one thing that you need to understand about related rate problems is when you have a measurement that never changes, that is not increasing or decreasing, that dimension can be put into the formula before taking the derivative. And that becomes very significant because if you can put it in before you take the derivative, then it makes taking the derivative that much easier. So we're going to use the Pythagorean theorem. So for part A, it says, how fast is the top of the ladder moving down the wall when the base is 7 feet from the wall? So here they're giving us that B is equal to 7, but no, that's changing. We don't know what A is, but they're asking us to find the change in A, dA over dt. How fast is the top of the ladder moving down the wall? They want us to figure out how fast that is when B is 7. And they're telling us that the base of the ladder is moving away from the wall at a rate of 2 feet per second. So they gave us dB over dt is equal to 2 feet per second. So they gave us a little bit of information there. We know we're going to use the Pythagorean theorem. A squared plus b squared equals c squared. So any measurement that's not changing, I can go ahead and plug in. So I'm allowed to go ahead and plug in c. So c is 25, so that would be 25 squared, which we know is 625. We don't know, well, a and b are both changing throughout the entire problem. So we can't plug into those until after we have taken the derivative. So if we take the derivative, we have 2a dA over dt plus 2b dB over dt equals the derivative of 625 will just be 0. And at this point we can start plugging in. Well, we've got 2 times, well, we don't know what a is, but we do know that c is 25 and b is 7. So couldn't I plug into the Pythagorean theorem a squared plus b squared, which is 7 squared, equals c squared, which is 25 squared? And if I do that math, a is going to be 24 feet. So I can use the information they gave me to figure out what some of the information is that I need. So a is 24. dA over dt, that's what we're trying to find. So we don't know what that is. Plus 2 times b they gave us was 7. And they told us dB over dt is 2. And that equals 0. So if we just do the math, we've got 48 dA over dt plus 2 times 7 is 14 times 2 is 28. So I'm going to go ahead and move that to the other side. That equals negative 28. And then if I divide by 48, I know that dA over dt is equal to negative 28 over 48, which is negative 7/12. And our unit of measure, since that is a length, that would be negative 7/12 feet per second. That is how fast the length of A is changing. The length of it is decreasing because this is negative 7/12 feet per second. For part B, it says find the rate at which the area of the rectangle is changing when the base of the ladder is 7 feet from the wall. Okay, so our measurements here are going to be the same. I still know that the ladder is consistent. It's not going to change. But this time we're using the area formula for a right triangle. Well, area is 1/2 base times height. And remember, your base and height have to form a right angle. So my base would be the b, 7, and my height would be my a value. Well, at first we didn't know a, but we found it here. A is 24. And they're asking us to find the rate at which the area of the triangle is changing. So they want us to find dA over dt. So if we take the derivative here, we're going to have to use the product rule. dA over dt is equal to 1/2. The derivative of the first thing is 1, so that's dB over dt, times the original second, h, plus the original first, 1/2 b, times the derivative of the second, dH over dt. And then we're going to plug in. dA over dt is equal to 1/2 times dB over dt. The change in b over time is still 2, times the height. Well, that's what we found for A. That's 24. Plus 1/2 times B. The length of B is still 7. Times dH over dt. This is where we're going to have to use the information that we found in part A. dA over dt, remember the height here is the same thing as your A value. So the change in dH over dt was negative 7/12. So I'm going to put times negative 7/12 here. So if I do the math, I've got dA over dt is equal to 24 plus negative 49 over 24. So dA over dt is equal to 527 over 24. And this is a change in area. So the unit of measure for area is going to be feet squared. So it's going to be feet squared per second. A pebble is tossed into a pond, causing circular ripples to form. The radius of the outer ripple is increasing at a steady pace of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the dispersed water changing? So in this one, they're asking us to find the change in area, dA over dt. This is the area of a circle, so our formula is area equals pi r squared. And if we're trying to find the change in area, we would take the derivative. That would be dA over dt equals 2 pi r times change in r over time, dr over dt, because we have to take the derivative implicitly. Now we're trying to find dA over dt. So if we look in the reading for the other information that they gave us, dA over dt is equal to 2 pi times r, when the radius is 4 foot, so they gave us that r is 4, and the change in r over time is 1. That was 1 foot per second. And so if we do the math, dA over dt is equal to 8 pi, and this is area, so that would be 8 pi. And if you think about the unit of measure, we're talking about area, and we're talking about change in area, and it would be feet squared per second. So that would be feet squared per second.